and the organizing committee for organizing this conference in a beautiful setting. I've never been to Alberta before, let alone Banff. It's gorgeous. Peter Cholak asked me to give a survey talk of the entire area. This will be a somewhat personal account, but also I noticed that the description of the conference on the website said that it started off with the sentence that reverse mathematics has gone far beyond the original foundational concerns of the founders of reverse mathematics, Friedman and Simpson. Maybe some of you were wondering what those foundational concerns were, so I'll say a little about that. It starts with Hilbert's 1900 problem list. Hilbert was one of the greatest mathematicians of his time, maybe the greatest, and in 1900 he formulated a list of definitive problems for the future of mathematics in the 20th century. Problems, and Hilbert, like many great mathematicians at the time, was intensely interested in foundations of mathematics. Things are a little different now, but at that time, all of the great mathematicians, Hilbert, Poincaré, all of them were von Neumann, all of them were interested in foundations of mathematics. And of the 23 problems on Hilbert's list, problems 1 and 2 belong squarely to foundations of mathematics. Cantor's problem on the continuum hypothesis, or the cardinal number of the continuum. These are Hilbert's titles for his problems. So one of the problems was titled Cantor's problem of the cardinal number of the continuum, and one was called compatibility of the arithmetical axioms. We would say consistency of the arithmetical axioms. Then also problems 10 and 17 are familiar to logicians. This Hilbert's 10th problem we know was shown to be unsolvable. One of the great unsolvability results, showing that a mathematical problem is unsolvable in the sense of Turing. And then expression of definite forms by sums of squares. You know this has to do, Hilbert's 17th problem, this has to do with real closed fields, and this problem sort of lives on in model theory today. In addition, problems 3, 4, and 5, which I'm not going to mention, were an outgrowth of Hilbert's interest in foundations of geometry. There's also, by the way, a 24th problem, which was discovered in some manuscript, which Hilbert never included in his list, but there's some manuscript of Hilbert mentioning the 24th problem. And when I read that problem, to me it says reverse mathematics, but I'll let you be the judge of that. So you can look that up. There's a paper that's available on this. Anyway, the second problem, consistency or compatibility of the arithmetical axioms, led to, or at least Gödel's incompleteness theorems were an answer to that problem. So let T be a theory in the predicate calculus. We're all familiar with these results of Gödel. First of all, satisfying certain mild conditions, like for instance it includes first order arithmetic, or actually much weaker systems. T is incomplete. The statement that T is consistent is not provable in T, so T cannot prove its own consistency. And then undecidability of the theory T. The problem of deciding whether a given sentence or formula is a theorem of T is algorithmically unsolvable in the sense of Turing. So this is also an outgrowth of Gödel's theorem, although Tarski, I guess, had a version of this result earlier. So some philosophers or would-be philosophers of mathematics believe that Gödel's incompleteness theorem shows the futility of the axiomatic method in mathematics. But we all know that the axiomatic method is essential for mathematics. And so I want to refute this and show, in fact, that Gödel's incompleteness theorem, especially the second incompleteness theorem, gives rise to a lot of structure which it reveals logical regularity in mathematics, even though the theories that we're interested in cannot prove their own consistency. This actually leads to a structure that is an interesting logical structure called the Gödel hierarchy. So I'll explain that. I'll see what role reverse mathematics plays here. Foundational consequences of reverse mathematics. This is an outline of the talk. One of the foundational consequences is a partial realization of Hilbert's program. Now, this is not mentioned in the list of problems, but Hilbert's program for finitization of mathematics beyond the big five and relationship to degrees of unsolvability. I'll talk about at the end. So the Gödel hierarchy. Let T1 and T2 be two series as above, as satisfying the mild conditions, which I did not spell out, and we'll define T1 to be less than T2 if the consistency of T1 is a theorem of T2. So T1 is not less than itself. That's the Gödel second incompleteness theorem. Now, usually this is equivalent to saying that T1 is interpretable in T2 and not vice versa. So it coincides, this ordering coincides with the interpretability ordering, usually, many times. It also many times coincides with the inclusion ordering, that T1 is included in T2, but not always. Now, the Gödel hierarchy is linear. So this gives a hierarchy of foundational theories, the Gödel hierarchy. The Gödel hierarchy is linear. That's an overstatement, of course. You can devise theories, and even some natural foundational theories that are incomparable. But many parts of the hierarchy are linear and exhibit other regularities, such as repeating patterns within this linear hierarchy of theories. So there's a lot of structure there. There's a lot of logical structure, and that's the Gödel hierarchy. And so the foundational or the axiomatic method is certainly not dead. In fact, the Gödel hierarchy contributes a central object of study for foundations of mathematics. So that's what I wanted to talk about. So this is a bird's eye, or 30,000 feet view of the Gödel hierarchy. It goes from very strong theories to very weak theories, and there's some theories in the middle. And this is just one hierarchy. Many mathematical logicians are working on some level of this hierarchy at different levels. Okay. So the set theorists tend to work up here with large cardinals. So super compact cardinals, measurable cardinals, things in between, wooden cardinals, and so on. Then there's a ZFC is a very natural stopping point because that sort of describes our intuitive understanding of sets as much as we understand as we are confident that we understand is formulated in the axioms of ZFC. Then there are weaker theories such as Zermelo set theory, simple type theory, which are also foundationally significant. Then I would say at medium strength are the second order arithmetic and various subsystems of it. Pi 1, 2 comprehension, Pi 1, 1 comprehension. I'll define these or mention them at least a little later. I'm going to define very little. A lot of you know, are very familiar with most of these items. Then I would classify as a weak theory, weak Koenig's lemma, RCA0 mentioned by Jeff already. Several of these theories have been mentioned by Jeff. The recursive comprehension axiom, primitive recursive arithmetic, elementary recursive arithmetic is weaker than that, and then various systems of bounded arithmetic. And going all the way down to the empty theory with no axioms. So these are various interesting stopping points in the Gödel hierarchy, and there are many other interesting stopping points in between. And if you look closely enough at this hierarchy, it's not really linear, but the big picture is that it's linear. So now what is foundations of mathematics? Foundations of mathematics is the study, I would define it this way, it's the study of the most basic concepts and logical structure of mathematics as a whole. Among the most basic mathematical concepts are such concepts as number, shape for geometry, set, function, algorithm, mathematical proof, mathematical definition, mathematical axiom, mathematical theorem, mathematical statement. These are fundamental mathematical concepts. The purpose of foundations of mathematics is to clarify these concepts. To understand what do we really mean by a number? What is a number, really? What is a shape? What is a set? What is a function, really, ultimately? What is an algorithm? What is a computable function? What is a mathematical proof? What counts as a mathematical proof? What is and is not a mathematical proof? What are the appropriate axioms for mathematics? That's the one down here. What do we mean by a mathematical definition? What do we mean by a theorem of mathematics? What kind of statements are mathematical and what statements are not mathematical? These are fundamental mathematical questions. Well, let me go back. So a question that reverse mathematics is designed to answer is, what are the appropriate axioms for mathematics in a certain sense? I mean, there are many meanings of the term appropriate here, and if you, for instance, from the viewpoint of set theoretic foundations, VFC is the appropriate set of axioms. But there are alternative viewpoints about foundations, and the motivation for reverse mathematics is that we want to look at axioms that are appropriate in the sense that they're just barely strong enough to prove the theorems that we want to prove. So appropriate means the appropriate axioms are those that are not excessively strong given the theorems that we want to prove. In other words, they're actually useful in proving mathematical theorems that we are concerned with. And it's been found that second-order arithmetic and its subsystems are a nice framework, an appropriate framework for studying this. So Z2, you're all familiar with this, so I don't need to go over this. But it's first-order arithmetic plus set variables, and you write down appropriate axioms for that. You write down sort of the obvious axioms that are true there. And within subsystems of second-order arithmetic, we can formalize rigorous mathematics. By mathematics, I mean talk about core mathematics, analysis, algebra, geometry, combinatorics, etc. I know combinatorics is going to be mentioned a lot at this meeting, and already has been in Jeff Hurst's talk. I'm not going to say too much about combinatorics in this talk. But because of reverse mathematics, subsystems of second-order arithmetic are now basic to our current understanding of the logical structure of mathematics. I think that's a fair statement. And the question that really interests me is, do we need very strong axioms? Do we need axioms way high up in the Gödel hierarchy in order to prove mathematical theorems? To what extent do we need those axioms? So that's to me one of the main questions that interests me from a philosophical point of view. Now, the subject goes back to Hilbert and Bernays in the Appendix 4 of their great work on foundations of mathematics. They basically present a formalization of rigorous mathematics within second-order arithmetic. They considered second-order arithmetic important, but they didn't look much at subsystems. So let tau be a mathematical theorem. Let S sub tau be a mathematical theorem, such as the fundamental theorem of calculus or whatever, some mathematical theorem that you might find in a mathematics textbook. Let S sub tau be the weakest natural subsystem of Z2, or second-order arithmetic, in which tau is provable. So we're taking the weakest axioms in which tau is provable. Now, some of the themes of reverse mathematics are, first of all, very often the axioms of S tau, the principal axiom of S tau, is equivalent to tau, logically equivalent to tau, over some weak base theory. So, in other words, we can actually determine the weakest natural system in a rigorous way using the predicate calculus, using mathematical logic. We can show that the principal axiom of S tau is equivalent to tau, and therefore it's not only the weakest natural system in which tau is provable, but it's the weakest system in which tau is provable. Furthermore, only a few subsystems of second-order arithmetic tend to arise repeatedly in this way. And again, this is a bird's-eye view. So here are two books on reverse mathematics. This Reverse Mathematics 2001 is a volume of papers that I edited that came out actually in 2005. Some of the authors of those papers are in this audience. Thank you very much for contributing to the volume. Then there's my book, Subsystems of Second-Order Arithmetic. This is going to be the second printing. The first printing came out in 1999, but went out of print about a year after that. The publisher did not anticipate the great demand for reverse mathematics. So the second printing is now in press. It's going to be published by the Association for Symbolic Logic and Cambridge University Press. All right. So in my book, the following 5 systems are emphasized. There's one chapter on each of these systems, because these are the big 5. These are the 5 systems that come up frequently, most frequently in reverse mathematics. So RCA0 is a kind of base theory, which you can think of as formalized computable mathematics. The smallest model of RCA0 is just the recursive sets, or the computable sets. Then, going beyond that, there's Weak-Koenig's lemma, which consists of computable mathematics plus the statement that every subtree of the tree 2 to the less than n, the full binary tree, if the tree is infinite, then there is an infinite path through the tree. So that's a compactness principle. So that's a weak version of Koenig's lemma, and that is a system that happens to come up frequently. Then there's ACA0, consisting of RCA0 plus the Turing jump operator. I'm listing these systems in order of increasing strength. So RCA0 plus the universe is closed under the Turing jump operator, or arithmetical comprehension. ATR0 says that not only is the universe closed under the Turing jump operator, but we can iterate the Turing jump operator starting at any set along any countable well ordering. And then finally, Pi-1-1 comprehension, which says that, which is much stronger than any of these. So in the book, I develop a table of what mathematical theorems are provable in which of these big 5 systems. And each of these x's represents a theorem saying that some theorems, a result saying that some theorems in the relevant area of mathematics are provable in some particular system. So for instance, there are some theorems, some fundamental theorems about separable Banach spaces are provable in RCA0. Others, you need to go up to WKL0 to prove them, and in fact, they are equivalent to WKL0, Weak-Koenig's lemma. Then there are others that you need Pi-1-1 comprehension to prove. And the blanks here means I don't know of any theorems in Banach space theory that are equivalent to arithmetical comprehension or arithmetical transfinite recursion. Well, that means there are maybe a couple different kinds of theorems there. In the version of this table that's in the book, each of these refers to a section of the book. Okay. So in abelian group theory, for instance, there's a lot of abelian group theory that you can just do in RCA0 computably, but then you need the Turing jump operator for some of it, you need arithmetical transfinite recursion for some of it, and you need Pi-1-1 comprehension for some of it. Down here in the miscellaneous, I have the Ramsey property, some theorems of Ramsey theory. And I must say, I looked at, my hope with looking at a lot of the infinite combinatorics, such as Ramsey's theorem, was that it would give examples of theorems that needed very, very strong axioms. And to a certain extent, that has been borne out. There are some generalizations of Ramsey's theorem that require pi-1-1 comprehension, for example. But, well, more on that later. So here's just a standard boilerplate list of standard theorems in reverse mathematics that are equivalent to WKL0. So each of these mathematical theorems, these are standard textbook theorems, are equivalent to Weak-Koenig's lemma over RCA0. The local existence theorem for solutions of differential equations. And so you have a differential equation, y prime equals f of xy, where f is a continuous function, and an initial condition, y of 0 equals 0, let's say, does this have a solution? That statement that has a solution is equivalent to Weak-Koenig's lemma. The Brouwer fixed-point theorem. Let's see, here are some more. There's a really remarkable number of theorems that are equivalent to Weak-Koenig's lemma. The separable Hahn-Banach theorem, Banach separation theorem in a separable Banach space about separating two disjoint convex open sets by a closed hyperplane. And in the combinatorics, there's this theorem. Every countable k-regular bipartite graph has a perfect matching. And I'm not giving any attributions for these, but some of the people in this room have proved some of these theorems. All the attributions are in my book. There's many people contributed to all this. Now for ACA0, here are some other mathematical theorems. And these theorems have to do, instead of compactness, they have to do with sequential compactness, many of them. So for instance, any sequence of points in a compact metric space has a convergent subsequence. That's provable in ACA0, and it implies ACA0. In fact, a special case just for sequences of real numbers in Euclidean space implies ACA0. Here's a statement in abelian group theory. Every countable abelian group has a unique divisible closure. The full Koenig's lemma, every infinite finitely branching tree has an infinite path. And as was mentioned, Ramsey's theorem. These are some other theorems equivalent, mathematical theorems equivalent to ACA0. Now here's some for ATR0. So those who have read my book are familiar with all these results. But the perfect, so I'd like to call attention to a couple of these theorems in the middle here. The perfect set theorem, every uncountable analytic set has a perfect subset. That's provable in ATR0, and the converse is also true even for the special case of closed sets. Every uncountable closed set has a perfect subset. That's equivalent to ATR0. Then Lewis' separation theorem, any two disjoint analytic sets can be separated by a Borel set. That's the basic theorem of descriptive set theory. I guess what I want to say is that the basic theory of Borel sets can be proved in ATR0. Some basic results about Borel and analytic sets. Some determinacy properties, a Ramsey type theorem, and here's a theorem from countable graph theory. Every countable bipartite graph admits a Koenig cover. That's I think this is going to come up later in a talk at this meeting. I think I saw one of the abstracts is going to mention some extensions of some conjectures and results on improvements of this result. And finally, for pi-1-1 comprehension, there are theorems about Borel equivalence relation, Borel sets, Borel equivalence relations, specifically Silber's theorem. Here's a theorem from Banach space theory about the existence of weak star closures in the dual of a separable Banach space. I guess that's enough. So those are the big five. So for those systems, and there are many more examples that I'm not mentioning. So for those five systems, we have many, many examples. So a large number of mathematical theorems fall into a small number of equivalence classes. The equivalence relation is logically equivalent over a weaker theory. Let's say RCA 0. So that tells you something about the logical structure of mathematics, in my opinion. Here I'm just so proud of my PhD students. This is a list of my PhD students who touched on reverse mathematics. Just want to point out that two of them are here: Alberto Marcone and Jeff Hurst, and Carl Mummert is here too, a third one. Yeah. So, this conference is wonderful. I'm seeing my whole life pass before me here. I mean, many phases of my life are represented by different people in this conference, like Tim Carlson there. Just a lot, people I've worked with in different ways. So some of the foundational consequences. First, as I've given examples of now, we precisely classify mathematical theorems according to which subsystems of Z2 they are provable in. So it gives you a nice logical structure, a picture of a nice logical structure within core mathematics. Second consequence, we identify certain subsystems of Z2 as being mathematically natural. A subsystem of Z2 is identified as mathematically natural if and only if it is the weakest system in which some mathematically natural theorem is provable. So at least it reduces it to the question of what's a mathematically natural theorem. And my answer to that is it's mathematically natural if it occurs in a core math textbook that wasn't written by a logician. Okay. Okay. And a third set of consequences is we work out the consequences of particular foundational doctrine. In other words, there are a lot of people over the years who have proposed different kinds of restrictions on mathematics. They're saying, well, impredicative mathematics isn't really legitimate somehow, or mathematics should be concerned exclusively with what's computable. That's another foundational doctrine. So instead of just arguing over these doctrines, let's try to see what would be the consequences of carrying out these doctrines. What if we were to outlaw all non-computable mathematics? What would be left? Okay. Well, so we get answers to those kind of questions from reverse mathematics. I mean, we know that certain theorems do not work in RCA 0, so therefore they're not true even in the minimum omega model of RCA 0. So we know that you need axioms beyond recursive comprehension to prove them, and therefore they cannot be part of computable mathematics. Another program is finitistic reductionism. Let's reduce all of mathematics to finitism. That's in a sense more radical, proposed by Hilbert. Bishop's constructivism is another point of view. Predicativity in the sense of Hermann Weyl, another great mathematician who was interested in foundations. And as pursued by Solomon Pfefferman. Predicative reductionism, that's I don't know if anybody's really proposed that as a foundational program, but there's this clear idea of what mathematics can be reduced to predicativism. Not maybe predicatively provable, but can we at least justify it somehow on the basis of predicativism? And then there's pi 1 analysis or impredicative analysis as pursued by Takeuchi and Schutte and Pohlers and others, many others. So we can analyze, and so I would say there's a rough correspondence between some of these programs and the Big Five. And therefore we have because of this work on the Big Five, we have a pretty good idea of what would be lost if we restricted mathematics in any one of these particular ways. We have a pretty good idea about that. So that's the kind of foundational consequences. Now let me just elaborate a little bit on one of these. So that's the big picture of reverse mathematics in my mind. Then that's the first half of my book. The second half of my book is a lot of technical theorems about subsystems of second-order arithmetic. Okay, one of these, let me elaborate a little bit on Hilbert's program. So Hilbert later proposed to, as an outgrowth of his concern for foundations, proposed to reduce all of mathematics to finitistic mathematics. That is, he wanted to, for instance, give a finitistic consistency proof for simple type theory, for example. Gödel's theorem implies that Hilbert's program cannot be realized in the form originally stated. For example, the statement that first-order arithmetic even is consistent is finitistically meaningful, but not finitistically provable. So, I mean, Hilbert certainly would have accepted this statement as finitistically meaningful, and he thought it was finitistically provable, but it isn't. So, the question is, what part of mathematics is reducible to finitism? And it turns out that there's actually quite a large part of mathematics that is reducible to finitism in a certain sense. And this is a reference to a paper. Now, this paper summarizes a lot of. It's an old paper of mine that summarizes a lot of results of myself and others on this question. So, just to give you the big picture of what happened there, first of all, Bill Tate argued in a paper on finitism, and sort of analyzing Hilbert's view of finitism, that PRA, primitive recursive arithmetic, is the embodiment of finitism. This is the formal system that captures what we mean by finitism. Then Harvey Friedman showed that WKL0 is conservative over PRA for pi02 sentences. And this class of sentences, pi02 sentences, includes all finitistically meaningful sentences. So any finitistic consequence of WKL0 is finitistically provable, is the paraphrase here. And by the way, this theorem of Friedman was proved model theoretically. Later, other people, I guess Wilfried Sieg and Ulrich Kohlenbach, who's here in the room, gave proof theoretic proofs of this. So, and that's important because it's important to give a finitistic proof of this conservation result. So then the third part of the realization of Hilbert's program is that, okay, we reduced Weak-Kernig's lemma, WKL0, to finitism. Then we have to show that a lot of core mathematics is provable in WKL0. So, and that is, those are the results that I was mentioning. Many theorems can be proved in WKL0, and many non-constructive theorems, such as the Brouwer fixed point theorem, and many non-constructive theorems. So Hilbert's program can be realized for a large part of core math, and that's and I sort of stridently argue for that position in this paper back in 1988. So that in other words, most people are saying Hilbert's program is dead. It's killed by Gödel's theorem, but that's not really true. No.
There's a path through the physics.
Well, in weak kernels, in WKL0, you can't prove that that tree is infinite. Yeah. The tree such that a path through it would give you a completion, give you a. I guess that's what you're talking about. Yeah. So the question is, why isn't my example of a finitistically meaningful theorem that's not finitistically provable, namely the consistency of first-order arithmetic? Why doesn't that fall under this scheme? And that's because it's simply not provable in WKL0. Okay. Well, that's correct. Yes. But so what I'm trying to say is that in that long list of non-constructive mathematical theorems that are proved in WKL0, all of their finitistic consequences are finitistically provable. So in that sense, we have a realization of Hilbert's program. All right. Now I want to move beyond the big five a little bit. There's been huge amounts of activity pointing out quite correctly that the big five isn't all there is to reverse mathematics. I mean, there are many more systems that are relevant. The big picture is not as simple as the big five would have us believe, and so I want to mention a few developments beyond the big five. Now, like I said, to me, the real question that motivated me to get interested in all this is, do we need really, really strong axioms in mathematics? Are really, really strong axioms ever useful? And we didn't have any good examples of core mathematics at the level of Pi 1-2 comprehension. And some of the work I did in combinatorics, like I got interested in Fresay's conjecture, for example, because I thought that maybe you would need Pi 1-2 comprehension to prove that. Turns out you don't. Other higher Ramsey results in sort of higher Ramsey theory, infinitary Ramsey theory. I thought that you would need strong axioms, but it turns out the axioms you need aren't as strong as all that. But we did, Carl Mummert and I did in 2005 come up with a example of reverse mathematics at the level of Pi 1-2 comprehension. So I'll just describe it very briefly. What we do is we set up general topology within subsystems of second-order arithmetic. So there's a sense in which you can talk about general topological spaces, not just Polish spaces or complete several metric spaces, but general topological spaces in subsystems of Z2. So here's the relevant definition. Let P be a poset, a partially ordered set. A filter is just what you think it is. It's a subset of P which is upward closed, and any two members of F have a lower bound belonging to F. And this is exactly the notion of filter that appears in axiomatic set theory. For instance, in Kunen's textbook of axiomatic set theory, where he talks about forcing, he defines a filter on a poset, and then he talks about generic filters. Now, we will not be concerned with generic filters. We're concerned with maximal filters. A maximal filter is an ultrafilter. It's a filter that is not properly included in any other filter. So, and then, this is a generalization of the Stone space. In other words, if P is the poset of non-zero elements of a Boolean algebra, then this is just the ultrafilters on that Boolean algebra. But it's a generalization because we're dealing with an arbitrary poset. So let MF of P be the space of all maximal filters. That is, the points of the space are the maximal filters. It's just like the Stone space. The topology, just like the Stone space, is generated by basic open sets determined by an element of the poset. So A typical basic open neighborhood is the set of maximal filters containing a particular element of the post set. Those are the neighborhoods. And we'll deal with MF spaces. So MF spaces are just spaces of this kind. Now, the point of this for second order arithmetic is if P is a countable post set, then we can formalize all this in second order arithmetic. That is, we can talk about filters, we can talk about maximal filters. We cannot form the set of all maximal filters, but we can talk about the space of maximal filters just like we talk about the real numbers in RCA0 or any complete separable metric spaces in my book. So this is so if P is countable, we say that MFP is countably based. But just stepping outside of second order arithmetic for a minute, what are the countably based MF spaces? Well, it turns out there's a result of Mummert and Stefan, which is saying that you can characterize these spaces. There's a topological characterization of what kind of spaces come up. Let me just give you a little idea of what this class of spaces is. It's a wide class of topological spaces. The countably based MF spaces, well, let's just talk about all MF spaces first. It includes all complete metric spaces and many non-metrizable spaces. So in particular, every Polish space is a countably based MF spaces, but there are also a lot of countably based MF spaces that are not metrizable. So this is general topology. It's not metric space theory. And so that portion of general topology for countably based MF spaces can be developed in subsystems of Z2. All right, now consider so in Karl Mummert's thesis there's a elaborate development of general topology in subsystems of Z2 in this setting. Now, consider the following metrization theorem. A countably based MF space is completely metrizable if and only if it is regular. To say a topological space is said to be regular if there is a basis of closed neighborhoods, or equivalently, if you have a point and a closed set, and the point does not belong to the closed set, then there's an open set surrounding the point and another open set surrounding the closed set, which are disjoint. It's a separation property for topological spaces. So a countably based MF space is completely metrizable if and only if it is regular. This is the right metrization theorem. This is a consequence of the Eurozone and Choquet metrization theorems in general topology. It's a special case. So this can be formalized as a sentence in the language of second order arithmetic, and then our result is this statement, MFMT, is equivalent to pi12 comprehension. Now the fly in the ointment is that we don't have this, the base theory that we use to get this equivalence is already quite strong, pi11 comprehension. We don't know how to weaken that. It should be possible to prove this equivalence in RCA0, but we haven't done that. So this is the first, and I thought this would be the beginning. You know, when we proved this, I thought this would be the beginning of a whole flood of reverse mathematics at the level of pi12 comprehension, but that hasn't happened. This is essentially the only example so far. So anyway, but we did go beyond the big five there. I just want to mention another set of another system that doesn't belong to the big five is weak Koenig's lemma. This is a system that is useful, introduced by another one of my PhD students in 1986, her PhD thesis, and it's a system that's between RCA0 and WKL0. It's very useful for the reverse mathematics of measure theory. So many statements of measure theory are equivalent to this axiom. And there's a good tie-in to Martin-Loth randomness, because weak Koenig's lemma is equivalent to, for all x, there exists a y such that y is Martin-Loth random relative to x. We realize that much later. So this is related to current and recent research in algorithmic randomness. Now, a second wave of research in the reverse mathematics of measure theory has to do with almost everywhere domination. This is a sort of natural recursion theoretic question. Say that a Turing oracle is almost everywhere dominating if for all x except the set of measures 0, and for all functions computable from x, there exists a function computable from B, such that which dominates the function from f. So for almost all x, every function computable from x is dominated by a function computable from B. In that case, we say B is almost everywhere dominating. And this turns out to be well. This is important. We realized that this was important. This is Dobrynin and I. We realized that this was important for the reverse mathematics of measure theory because, for instance, B is almost everywhere dominating. Actually, this result is due to Choate, Hansen, Miller, and Solomon, but we proved a similar result. Every pi02 set contains a pi01 relative to B set of almost the same measure. And there's a paper, I believe it's still in progress, by Choate, Hansen, Miller, and Solomon that they clean all this up and work out this reverse mathematics and prove a lot of very important, interesting results about almost everywhere domination. This turns out to be related to LR reducibility in the sense of Andre Nice. The Nice's definition is A is LR reducible to B if every x which is Martin-Luff random relative to B is random relative to A. And that's an interesting reducibility notion. And there's been many interesting theorems proved about that. So that's another good tie-in to recent research on algorithmic randomness. So I want to say that algorithmic randomness has some good connections to reverse mathematics. I'm running out of time. Wanted to say something about degrees of unsolvability. Let me just say this, that all of you who work in this field know that there are close connections between degrees of unsolvability and reverse mathematics. I mean, the way I look at it is reverse mathematics kind of gives you a way to package results and degrees of unsolvability in a way that says something about it's sort of the significance for foundations of mathematics is more accessible, more easy to understand. But what kind of degrees of unsolvability do we want to deal with? I claim that Turing degrees are too restricted. RCA0 corresponds to the Turing degree 0, sure. ACA0 corresponds to the jump operator, or the Turing degree 0 prime, or maybe the omega jump. Pi11 comprehension corresponds to Kleene O, or maybe the omega's hyperjump. And Pi12 comprehension also corresponds to a particular Turing degree. But it is difficult to assign Turing degrees to systems such as WKL0, WWKL0, ATR0, etc. They don't have specific Turing degrees associated to them. And I want to say that Muchnik degrees, I guess you all knew this was coming, if some of you knew this was coming. I want to say that Muchnik degrees are the right concept of degrees of unsolvability to use here. I don't have time to define it, but this is a generalization of Turing degrees. And there's that picture, but I don't have time. But the point is, the lattice of Muchnik degrees contains many degrees which are relevant for reverse mathematics and relevant for the kind of stuff we're doing in this conference, such as the Ramsey. So look at the problem of finding a real which computes homogeneous sets for all recursive colorings of pairs. That's most naturally viewed as a math problem, and its degree is therefore a Muchnik degree. So that's an example. Almost everywhere domination also gives rise to a Muchnik degree, and randomness gives rise to a Muchnik degree. R1 is the Muchnik degree of the one random reals, the Martin-Luff random reals. So Muchnik degrees are a degree structure which is more relevant to reverse mathematics, I think, than Turing degrees. In Turing degrees, the only natural examples of degrees are 0, 0 prime, 0 double prime, etc. But in the Muchnick degrees, there are many other natural examples of degrees. So, and they answer the kind of questions we want. So I just want to make a little propaganda for my current research interest, Muchnick degrees. Thank you. Time for any questions? Oh, the picture? By the way, this is a picture of the Muchnick degrees associated with pi01 subsets of 2 to the non-empty pi01 subsets of 2 to the omega. And you see, even in that very restricted sublattice of the Muchnick degrees, there are many interesting examples. Every one of these black dots, except for this one, is an interesting Muchnick degree. Maybe that one's interesting because it's the only one that's not interesting. I want to say that the lattice of Muchnick degrees, Bjorn has this very elaborate, well, you saw the diagram that Jeff showed. Bjorn has a very, very elaborate diagram of, he doesn't call them Muchnick degrees, but they're Muchnick degrees. It's got hundreds of points in it. It's just a lattice pointing out some of the interesting Muchnick degrees that there are. I don't know. I could tell you what some of these are. R1 is the one corresponding to weak Koenig's lemma. 1 is the one corresponding to weak Koenig's lemma, WKL. So there are. It's a big subject.